All right, so today we start talking about the magnetism. We learned about the electricity before, and we learned about the charges. We learned about how the charges behave. We learned about the properties of the charges. And then when the charge starts moving, we talked about the electric current. Now here we're going to talk about the magnetism, and then later we will talk about the combination of the two, electricity and the magnetism. Now the magnetism plays a very important role in our everyday life, and if you look at these beautiful color pictures, so these color pictures tell us that how beautiful the phenomena we can see in nature. So these beautiful colorful phenomena, they are all the combination of the electricity and magnetism, and we call them the northern lights. We'll talk about that when we go further. So now also, not only this, by learning the magnetism, we not only will learn what is the cause of the northern lights, but we will also learn how does the earth protects us from the solar wind and the cosmic rays due to the magnetic field of the earth. Now, when we talk about the north or the south, we are really going to learn today that when we say we are going towards north or going towards south, are we really talking about the north, geographical north, or we are just following the compass needle of the magnet. But before I go further, make sure we know the following stuff. Remind ourselves about the electric field, which we talk about in chapter number 17 and 18, basically. Then what are the charge objects, and these charge objects provide the electric field, and this electric field, you can find the presence of the electric field by the electrical forces, right? We need to also know remind ourselves the direction of the electric current in the circuit. That's what we learned in the chapter number 19 and previous chapter, and we also learned about the Newton's laws of motion, and one of them, the Newton's second law of motion. That is very important, but we learned about force applied on a mass m, object of mass m, and acceleration produced in the direction of the force. So we'll talk about all these things, combine all these things over here in this chapter, right? So this is your chapter number 5 or 6 in your book. Now, we learned about the charged objects. The charged objects, the charges, either there are two kinds of charges, either they repel each other or attract each other, okay? Now, similar way, we will talk about the magnets. So the magnets have the two poles, then these two poles of the magnets are similar to the electrical charges, but the electrical charges by itself, they do not show the properties of the electric field, about the magnetism, right? They just show you the charge. Then by the charge itself does not tell you anything about the magnetic field, right? So we will learn over here as well that what will happen to the charges if we start moving the charge. Is there an electric field, the magnetic field? So then, which means we will try to learn that is the electricity and magnetism, they are correlated with each other, or they are connected with each other some way or the other, or there is totally unrelated phenomena, okay? So in this chapter, basically, we will not only learn about the magnetisms, what are the magnets and the properties of the magnets, but we will also learn the connection between the electricity and the magnetism. And the connection of the electricity and magnetism makes it more fun, okay? Now, let's talk about the magnetism first. What is magnets? So in the old times, people used to talk about, in the ancient times, they talk about the magnetism, they come from the lodestones. which is the lodestones are naturally magnetized pieces of iron. And this is what we are talking about 800 before Christ. They called magnetite. Now, the word magnet is a Greek word. This means the stones from Magnesia. So this is the place in the map, right, called Magnesia. So the stones from Magnesia. Now, this is a part of the ancient Greece, right, where these lodestones or magnetites were found. Now, the materials that can be magnetized are called the ferromagnets. Those are iron, nickel, cobalt, etc. And then, what the magnet do? The magnets have the magnetic force, just the charges have an electric force. So with this magnetic force, when it is bring close to these materials, like iron, nickel, cobalt, so these materials are attracted towards the magnets, or the magnets, when they were brought the similar magnets close to each other, they will either attract or repel each other. So the magnets produce the magnetic field just like the charge produces the electric field. Okay, so there is a quite resemblance between the two. Okay, that charge produces an electric field, magnets produce a magnetic field. The like charges repel each other, unlike charges attract each other. And now we'll talk about the magnets the similar way. So we have two kinds of electric charge, positive and the negative charges. Like charges, as I said, repel, the opposite charges attract. Similarly, two kinds of magnets, or we call the two kinds of magnetic poles. Okay, to be correct, one is called the north pole of the magnet, the other is called the south pole of the magnet. As you see over here, the north pole and the south pole. Each magnet has two poles, north pole and south pole. When you bring two magnets closer to each other, the like poles of the magnet will repel each other, whereas the unlike poles will attract each other, as in the case of the charges, right? Here you see the positive and negative charge attract each other, whereas negative and negative repel each other. Here you see the south pole and the south pole of the magnet repel each other, whereas the north pole and the south pole of the magnet, they attract each other. However, in the case of the charges, we can, as we said, the conservation of charges, whenever you have a positive charge, you can separate, then you can, other object, when the objects rub against each other, one object will become the positively charged, whereas the other object will become the negatively charged. However, we can separate these charges some way that two objects which are oppositely charged, after charging them oppositely, one object get one kind of charge, other can get another kind of charge. I can separate those charged objects. It means I can have a positive charge and a negative charge on the two separate conducting objects. Alright? The spheres, as we saw in the previous chapter. However, we cannot do the same thing for the magnetic poles. Alright? There is no such thing so far that we can separate the north pole of a magnet or the south pole of a magnet. If I cut the magnet into a half, then each magnet by itself realign in such a way that it will make a north and a south pole. Then I cut this magnet again into half, then I will have another magnet which make a north and a south pole, so on and so forth. How many times I cut, I keep chopping it, I will getting a north and the south pole of the magnet. However, the theories suggest there is a separate poles can exist, but that is just a theory which is called the monopole. So in other words, we haven't seen the magnetic monopoles yet. Electricity and magnetism theories tell us they exist, but if you happen to find it, this will be a Nobel Prize discovery, right? And you can see this then this is a Nobel Prize discovery, and if you don't think that is something you haven't done useful, so it can get you a Nobel Prize, and if you get a Nobel Prize, that's a great achievement for your life, right? Now, for the magnetic field, just like for the charges, the region, the vicinity around a charge is called the electric charge. Similarly, the region, the vicinity, the area around the magnet is called the magnetic field. All right. So the electric field is represented with the letter E, and this is radially outward. If you have a point charge, as you see over here, it goes from the electric field lines by convention go from positive charge to the negative charge. Similarly, if I have a bar magnet, okay, the bar magnet also exhibits the magnetic field. Since the electric field is a vector quantity, magnetic field is also a vector quantity. Electric field is represented with the letter E in the textbooks. The magnetic field will be represented with the letter B. Alright, this is also a vector. And if you look at this picture, so I have a magnet, I chop this magnet into pieces. And you see, when I chop it, each piece becomes a north and a south pole, and they attract each other. And then when I rotate this, these becomes the like poles. Now they become the unlike poles, okay, where they repel each other, okay. So here there is an attraction between the magnetic poles, and here is an attraction between the magnetic poles, no matter how many pieces I chop into. Here is the magnetic field line, go from here is a horseshoe magnet, north and south pole, and south and north pole. The magnetic field line seems to originate from the north and go to the south pole. Alright? Now, if I bring after chopping, I bring the similar poles together, you see that they repel each other. As you see over here, north pole and north pole, they repel each other, whereas north and south pole, they attract each other. So unlike poles attract each other, repel each other, as you see over here, the unlike poles, and you will find a place in between where there is no magnetic field, right? Whereas the like poles, they attract each other. Alright? Now, in order to find the direction of the magnetic field, in the labs, you use the compass needle, and if you put the compass needle around the bar magnet, and you will start seeing the direction of the compass needle will keep changing. Close to the north pole, you see the south end of the compass needle, and as you go, this is deflected like this, and here the magnetic field lines are parallel, in just like a vector in the case of the electric field from positive to the negative. Here is the north to south. Okay. Now we can draw the magnetic field line using the compass needle. All right. That will tell us the direction of the magnetic field. So we can sketch the magnetic field line. Okay. As you see in the picture B, and the direction of the magnetic field line, as you see, is from north to south. Okay. Now the magnetic field, as I said, is represented with the letter B. That is the magnetic field. And this is as a unit of Tesla. Now nowadays it's much easier to remember Tesla because you see the Tesla cars, alright? So this is a standard unit for the magnetic field, the Tesla, okay? However, this is a bigger unit. We'll talk about that, smaller units, when we get further there. Again, here you see the magnetic field lines using the compass needle. We can draw, see the colors. If you take the compass needle, one of the side of the compass needle is colored, other one is almost white, and the colored sides, or the red colored side, is usually the north side, to represent the north, and then the other one shows the south. Okay, so if you look at this, the magnetic field lines again go from the north to south. That's how we draw it. In the lab, we can see how the magnetic field lines can be drawn, right? As you see over here, the magnetic field lines can be drawn up there. Now, how about the connection between the electric field, electric charges and the magnetic field, magnetic field or the magnets. Okay, so the electrically charged objects do not interact with the magnets in the same way as the magnets interact with each other. All right, so this is a very interesting phenomenon. The magnetic poles are not the electrical charges. Okay, for example, here I have the magnet bar, north pole of the magnet and the south pole of the magnet. I have a charged foam ball, right? So when this is hanging with the thread, when I bring the positively charged foam ball closer to the north pole of the magnet, it is being attracted. On the other hand, if I bring it close to the south pole, it's being attracted. So the magnetic bars interact with the charges, but not at the same way as the charges itself. Okay, so the magnets and the charges, they interact with each other with a different way, but they still interact. All right. Now the question is, what is the source of the magnetic field if not the magnetic charge? Now it means something is different. What is that different? When you put the electric charge in motion, all right, which means the current through a wire, current carrying wire, all right, so that will produce an effect of a bar magnet. So when I say a solenoid, the solenoid is something like a coiled spring wires. So when the current flows through them, so the ends of the solenoid, they will behave like when the current flows through them, they will produce a magnetic field, and one end of that solenoid become north pole and the other will become the south pole. Okay, so we need to understand the source of the magnetic field generated by the bar magnets. Okay, in this understanding, we can think of the atomic level within the bulk of the matter. So if you look at that, so here is the structure of the atom. As we know, the central part is the nucleus, which is proton and neutron, and the surrounding is the electron revolving around it. Now when the electron is revolving around the proton and nucleus and the neutron around the center of the atom, it is spinning. So it moves, it keeps moving around it, but at the same time it spins around it. Okay, so which means the electric charge not only moving, it's spinning. When it's spinning up and down, dancing like that, so it changes the direction of the magnetic field as well. Okay, so that spin play an important role in the changing the direction of the magnetic field when the electron is orbiting around the nucleus. So here is another example which we can perform even at home. If you take the coil, the wire wound around the steel nail, and connect this wire while it is wounded around the steel nail, and right now it's not a magnet. I can turn this into magnet by connecting to the battery, then the current will flow through the coil, and then you will see this steel nail will start attracting the metal objects, so that will become a magnet. All right, so if I remove this battery, then the steel nail will not be a magnet for a longer period of time. It will demagnetize again. All right, now there are other sources of the magnetic field. In 16th century, Gilbert told us that the earth has a giant magnet. So how did we know? He mapped out the earth's magnetic field. As you see, earth is also moving around the sun, right? Orbiting around the sun, at the same time it's spinning, right? It's orbiting around its center. So now the magnetic field lines go from the geographical south to the geographical north, right? So he said there is a big giant magnet. It looks like, well, the earth is rotating, it's made of atoms. So then it behaves like there is a giant big magnet in the center of the earth, and this giant magnet is such a way that the north pole of the magnet is on the geographic south, whereas the south pole of this giant big magnet is at the geographic north. So when we say we are going towards north, so that is basically geographical north is not a magnetic north, it is a magnetic south. And when we say we are going towards south, that is we are talking about the geographical south, right? But that is over there, you see that there is a north pole of the magnet. Now if I bring the compass needle, you will see the north pole of the north end of the compass needle will points you towards the geographical north, okay? Because over there is a south pole of the magnet. Alright, now, so the earth has a magnetic field. How about the sun? Sun is also, like the earth, generates a magnetic field, right? Because there are chemical processes going on, hydrogen is converting to helium, and the charged particle moving. As a result, we have the magnetic field which is generated on the earth. The spots on the sun, sometimes you will see, if you ever had a chance to look at the sun closely by the solar telescope, you will see the dark spots on the sun. That is the area where is a huge magnetic activity is going on the Earth's sun's magnetic field. So sun is sun is also the big source of magnetic field. Earth is a magnetic field. These flares tells you that the magnetic field is being generated over there, right? Now, the sun by itself is a hot soup of the charged particles, the hot gas soup, right, called plasma, charged particles. So that is a source of magnetic field. Now here, the magnetic field B is represented with the letter B, as I said. Now the direction of the magnetic field at a particular location is defined by the direction of the north pole of the compass needle and points to at the location, okay? The magnetic field vector at the location is a tangent, alright? So if you look at this, the magnetic field vector is a tangent to the direction of the magnetic field lines, right? So here, the same way is here, so, right? Same way is here, so magnetic field lines go there like this, north to south, okay? So, when you go closer to the area or the region of the poles of the magnet, you will see the stronger effect of the magnetic field. If you go away from the poles of the magnet, the effect of the magnetic field will be smaller and smaller. Alright? Now, in the case of the electric field, we have the charge distribution creates the electric field, and the electric field is responsible for the electric force, right? In order to see the effect of the electric field, we use this equation, F is equal to the electric force is equal to the charge times the electric field, right? I bring the test charge close to that. Now, for the magnetic field, what is this? So, in the magnetic field, moving charges are the currents in an electrical wire that creates a magnetic field. If I take electrical wire or running around this room, you take the compass needle close to this wire, you will see the deflection of the magnetic field over there. Okay? Now, the field, there is a magnetic field around it in the space, in the vicinity around the magnet. So that is called the magnetic field, and that magnetic field exerts a force F on the moving charge. The charge is moving through the wire, alright? And that is called the force law, alright? So, first time in 1819, the Danish physicist Hans Ørsted that pointed to us that the magnetic needle responds to the current carrying wire, right? That is the link between the magnetic field and the electricity. So another familiar source of the magnetic field is the electric charge moving through the external magnetic field. For example, here I have a horseshoe magnet. If a charge passes through that, if a positively charged, that will be deflected. Negatively charged will be deflected. If it's a neutral charge, like a neutron, that will not be affected. So when a moving charge passes through the magnetic field, it changes the path. So what is going on? It means there is a magnetic field produced by the moving charge, and that magnetic field is going to be affected by the external magnet, just like this horseshoe magnet, and that will affect the magnetic field. The two magnetic fields interfere each other, and as a result we will get the magnetic field effect on the charge. Here is a direction. Here is another thing. The electric bulb connected to the battery, switch is open. If I put the magnetic compass needle below and above the wire, I don't see anything. This is pointing towards the geographic north and geographic south. On the other hand, if I close the switch, then there is a direction of the current flowing from the positive terminal of the battery to the negative, and you see that there is a deflection in the current. So it means there is a south pole of the magnet created by the current, and then there is a deflection here under the wire, and the deflection over the wire is in the opposite direction. Alright, so it means the direction of the magnetic field when the current moves through the wire changes. Alright, so that is another important phenomenon which we want to see. So the electric current is generated. It means if I look at that, now if I hold this wire, right, so then in my right hand, while in the flow of the direction of the current, alright, so what is going to happen is, so I can feel the direction of the electric field, the left hand. So you see the current is flowing through from positive terminal, so my thumb pointing in the direction of the current, and my curled finger will be pointing in the direction of the magnetic field. Below the wire, the magnetic field north pole is here, and above the wire, the north pole is the magnetic field direction going from this way. I mean going from north to south. North to south from the top, and north to south from the bottom. So the up, top and the bottom of the wire, the magnetic field changes. So to summarize here, so we can see a charged particle. If I have the charged particle in my moving in an external magnetic field, this charged particle will experience a force which is called the magnetic force, and it depends on the velocity of the force and the direction of the external magnetic field. Alright, now how do I determine this? So if it's a positively charged particle, I take the right hand and hold my fingers, right, put the charge over here on the palm, and in the direction of the current, the motion of the charge, and then move towards the external magnetic field. The thumb will point where the charged particle will go. Alright, so F is equal to QVB, that is the magnetic force. Okay, we started introducing the magnetic force over here.